Welcome to the Rare Earth Exchanges podcast, where power, politics, and the world's most coveted materials collide. Rare earth elements power the backbone of tomorrow's most critical technologies. With China dominating global production, the U.S. and its allies must align strategically to ensure a stable future. This urgency prompted tech entrepreneurs Daniel O'Connor and Dustin Olson to launch Rare Earth Exchanges, a news and insight platform built to equip stakeholders and decision makers with the tools and intelligence needed to reduce dependency and build prosperous resilience. Let's get into it.
Hey everyone, welcome back to the Rare Earth Exchanges podcast. We're excited you're here. I'm your host, Dustin, joined by my co-host, Daniel. And today's guest is Aaron Noble, who is a professor and department head of mining and minerals engineering at Virginia Tech. Aaron, welcome to the show. How are you doing?
Welcome. Doing great, guys. Really glad to be on the show. I've been following your work for a couple of years now, and it's an absolute honor to be on here. So looking forward to the conversation today.
Yeah, we are thrilled to get your perspective on here. And we were introduced to you through somebody else that we had on the show. And so we're excited. So to kind of start us off, Aaron, you've described rare earth elements. You've likened it to like cinnamon and nutmeg, ingredients in a cake, a really nice cake, but you don't really appreciate it until they're missing. It's almost salt too. If you don't have salt in the food, you don't appreciate it until it's not there. And so I like that comparison that you have of how embedded simple things are in a normal thing in life, and you don't realize it's gone, or you don't realize it's missing until it's gone. So can you just explain a bit more and help people understand, I guess, the importance of rare earths?
No, that's a great question, Dustin. And fundamentally at heart, I am a teacher, right? As a professor, I like to think I'm a teacher. And as that, I like to take, one of the principles in teaching is if you can take a concept and make it memorable, right? Then that's how you build some robust knowledge in the people that you're teaching. And in this rare earth landscape, I feel a need to teach the public, right? There's a lot that people don't know. There's a lot of ambiguity. And so anytime we get an opportunity to take this and kind of break it down in a way that's understandable and memorable and relevant, I like to do that. And through the years, I kind of came up with this cake analogy. And I initially heard it from another professor at another university, so I can't take credit for the original idea. But I do think in one of the talks I gave before, it certainly had the best artistic depiction, right? They actually had a nice like cake put up on the screen while I was talking, which was really fun to watch. And also I was saying I personally don't like desserts. It's odd. I use that analogy, but I'm not a fan of desserts. But if you take material needs in society, right? And the way that kind of analogy works out, you imagine our material needs and our mind resource needs, and you envision that being a cake, right? The bulk of the cake it are not the spices, right? It's the nut, or it's the flour, the eggs, the milk. And I like to think of that being the aluminum, the iron ore, the crushed stone. Like if we think of the fundamental building blocks of society and the big mass of material in society, that's your flour and your eggs. It's aluminum, it's crushed stone, it's your base metals. But if society, if you had a cake that was only flour and eggs, it wouldn't taste very good, right? It wouldn't be a very good cake. And the same way, if we had a society that was just built with iron ore and crushed stone, we'd be living in the Middle Ages, and it wouldn't be a very interesting society. So the rare earths are the spices in the cake. They're the nutmeg, they're the cinnamon, they're the salt. Not very high in volume, but the things that bring out all the flavor and all the joy and all the modern conveniences that we have. And the cool thing about this is that analogy sits at surface level, right? And I think people really can appreciate that. Whether we like it or not is one thing, but we've all eaten a cake and we've all eaten a good cake probably, so we can resonate with that. But there's also some subtlety to this, right? There's another layer that I actually think reveals the fundamental challenge enabling rare earth production in this country. And this is the second layer of the analogy that I don't get to very often, but now's a good opportunity. And what it is, there's a plot, and you can envision this plot in your head. Let's take all the commodities, right? Like all the mine commodities, And let's look at how much is produced on one axis, like tons of production globally, and then how much it's worth. Like, what does it sell for typically, right? And if you multiply those two together, you can get almost like a market cap. Like, how much is this commodity worth globally? And if you look at your flour and your eggs, right? What are your really big commodities in the world? You can think about iron, aluminum, copper, gold. Like, these are the biggest commodities in terms of market share, and these are hundreds of billions of dollars or I should say market cap, hundreds of billions of dollars of market cap. So the global iron ore industry, right? Iron ore, you could say nominally we produce billions of tons a year at $100 a ton. So that's hundreds of billions of dollars in iron ore in that commodity sector. Interestingly, gold's almost the same market cap, except it's on the other side, right? So it's a very low volume, high value good, but still in that $100 to $500 billion range. If you look at the rare earths, you got to work pretty far down that curve. And I'd say the best rare earths are hundreds of millions of dollars. And something like samarium is like $10 million. And it's like I've sat in rooms with people who could buy the global samarium supply with their personal bank account, right? And to me, it's a very obvious thing to know. I think we all know these are small, specialized markets. But the implication then is, on my side as an educator and as someone who thinks about technology, where do we educate people, right? Do I educate my students to go into base metals and crush stone, or to go into really specialized metals, right? And if I've got an investment dollar that I can put into an R&D project, do I put it into a $500 billion market or a $10 million market? So it creates this like negative feedback loop that I think really stands as a fundamental challenge. So the cinnamon and the nutmeg analogy, I think it lands well, right? We can all appreciate that. But underneath it, thinking about the implications, this is why development and advancement in the sector is so challenging.
Well said. I think the visual is very strong, and I think most people enjoy eating, especially desserts. So I think that's great.
Yeah, on that note, we started this show and the website end of 2024, so it's been a little bit over a year and a half. We've learned a lot. I think we've helped shine a light on this a little bit, at least. Interesting from your perspective, because you've been at this for some time now. These spices that you mentioned are extremely important. Okay, and um, as we know, much of the industry today depends on, albeit small amounts, but nonetheless amounts of these inputs. How long, in the academic world, have we known that this is a mounting problem, or has it been that, sort of the ideology of much of the last decades was, oh, we just outsource this here and there and things sort of magically happen? Could you provide to the audience sort of just a higher level view of the last few decades and how thinking has maybe changed?
It's really a really good question. And like I said, I've been kind of really active in the rare earth teaching and research space since about 2015. So my trajectory has been interesting. I was not active during the initial rare earth crisis of the early 2010s. I was still a student then, pretty active in mineral processing. But if you asked me to name three of the rare earths, I wouldn't have even gotten one, right? And it was like, and I did pretty good as a student, and I wouldn't have gotten one, you know. And so my perspective is kind of in this last 10 years predominantly, and then before that, though, there's interesting historical perspective. And one of the quotes I used to show on my on one of my slides that commonly, we've talked a lot about recovering rare earths from unconventional sources like mine tailings, acid mine drainage, and fly ash. And there's this famous quote from a Penn State professor in the 1950s, like the 1950s, and they were doing like prognostication on what the world would be like in the year 2000. Right? I guess that was fun at the turn of the century, but. In the 1950s, and what the quote says, geochemists have found notable concentrations of germanium in the rare earths in fly ash. By the year 2020, we will not be wasting those. We will be recovering them. And it's really interesting to think about, right? Because it's like, at the time, right, this notion of even waste valorization and reutilization was pretty weak. It was pretty nascent. At the same time, the rare earth industry was very nascent, right? Like we weren't using a lot of rare earths for magnets and things like that. And Mountain Pass was the leading supplier. So it's a really interesting quote. Now we didn't make it by 2020, and so we still got a ways to go. But I'm going to say at least on order of magnitude, we were headed in the right direction. But yeah, this notion of criticality, I think, has become common over, we'll say, the 10 years I've been kind of engaged. I go back to, right after the first rare earth crisis in 2010, I think it was 2012, 2013, Department of Energy published a critical mineral strategy report. And this was one of the first references I've seen where they actually took a critical look at the two main measures of criticality, one being potential for disruption and two being importance to, in this case, energy technology. So you look at supply risk and demand pull, and you put those together, and you can come up with an indicator of criticality. And that report that I think, like I said, was 2012, 2013, was really the first time I saw that articulated in that manner. We've known that minerals are essential forever, right? That's been the calling card of mining going back to the dawn of humanity. But this notion of criticality, I think, really came very present after the 2010 rare earth crisis. And then we've seen the maturity in those discussions evolve, since I've been engaged.
Makes sense. Makes sense. Because again, one of the things that we've been sort of a hypothesis is that efficiency was the driving factor in global economies over, maybe 1950s through to 2000, 2010. And now supply chains become ever more important, and resilience is being emphasized. And to have resilience, you need to have control of your supply chains, which means even these small little spices for the cake we need to control. And so on that, we've been big on industrial policy and trying to find ways to raise awareness. And our paths have crossed a while ago, and again, grateful for all you're doing. From that standpoint, are you, based at both at your university and at others, are you starting to find that there's an interest in industry again, in mining, metallurgy? Are you starting to see any changes among young people?
Really good question, Daniel. And if you had asked me, I would say 12 months ago, I would have said no, right? And I think we're seeing some marginal uptake in interest, but I would say over the last 12 months, we are on a very dynamic portion of that curve. And so it's I would say it's hard to tell. And the reason for that is actually this boom in AI, right? And if you look kind of historically, not at mining engineering, but across all engineering disciplines, right? Like mechanical, electrical, civil. If you take all the engineering disciplines, but you take computer-facing disciplines out, and we look at enrollment trends in the U.S., the peak enrollment actually came in like 2016 and 2017. And we've been dropping by about 15,000 students nationwide a year in engineering. That's been the trend. So over the past decade, the number of engineering students has gone down by about 15,000 a year in the non-computing disciplines. Now, the computing disciplines are on this exponential takeoff, right? So they were much lower, but you look at the trend, they were like on this exponential takeoff. Now, the interesting thing when you layer that back, right? So what's the subtlety? What's the second layer of this cake? If you look at the peak time in different engineering disciplines, right? So when did each engineering discipline hit their peak? I think what you see notionally is that the more vocational industry related disciplines peaked first. So mining would have been like 2014. Petroleum probably peaked a little bit before that. Then mining. Actually, it was probably nuclear, then petroleum, then mining, then metallurgy, then civil, then mechanical. Like that was kind of the order in which they hit their peak and then started declining. And then, but what you've seen now, like in the last cycle, right? I can tell you here at Virginia Tech, application demand for students in computer science is significantly lower than it was a couple years ago. And where we now see growth are in the vocational disciplines, right? So construction engineering, mining engineering, metallurgy, mechanical, civil. So it's almost like we're going through the reverse cycle. We are on the very beginning leading edge of this. So I'm really curious to see how that plays out. But from kind of like you said, this larger holistic policy view, are we seeing some self-reversion in the system around people leaving the computing disciplines and going back to the vocational disciplines? Is that happening naturally? Early signs are yes. Let's see how sustainable it is.
Great, great. That's a great answer. Dustin, I have some more questions, but please chime in.
Yeah, I think, first of all, I think it's great that people are finding more interest in these vocational disciplines, as you're saying. No surprise that because of AI, people are leaving the computing disciplines. I think that's a fascinating stat, but I'd be interested to hear a bit more about the $10 million DOE research fund that you're managing there at Virginia Tech and what that is allowing you guys to do, what it's unlocking, what doors is it opening?
Yeah, so the project in question is funded by the U.S. Department of Energy through their Core CM program. So Core is carbon ore, rare earths, and critical minerals. They call it Core CM program, and then our specific project is called Expand Appalachia, and that's a project. The project principal investigator, the lead here is Dr. Richard Bishop, one of my colleagues, and then I'm co-leading it with him. And through the Core CM program, what the Department of Energy did is they kind of took the entire US and then broke it up into regions and roughly following some geologic trend. And the region of interest for us was called the Appalachian region. For me, I would probably call it the Greater Appalachian region, because if you draw the boundary, it goes from Tennessee to Maine and is inclusive of like every state that you would draw from Tennessee to Maine, from Memphis all the way up to Arcadia National Park, right? So that would be Greater Appalachia in that sense. And what we've been charged to do is to kind of identify the critical mineral potential within that region broadly. And so a big portion of this is understanding existing data sets. So are there data sets that identify and quantify resources in the ground, I would say? So kind of conventional ore type resources and this broader base of unconventional resources. So mine tailings, former, industrial waste sites, acid mine drainage, fly ash, pretty broad in that scope. And then the material scope that we're looking at is rare earths, anything on DOE's critical mineral list, and carbon ore. So if you look at the scope of the project, it's actually pretty significant in that there's a large geographic study area, there's a large base of resource we want to quantify, and then there's also a pretty large, material categories that we're looking at. And then thinking broadly about it, so we try to be innovative, and we think, it's like how can we identify potential targets of opportunity quickly. So we do have a rubric-based approach, somewhat of a rigorous-based approach, I would say, and looking at, economic potential, social suitability, right? Like, is this in a national park? Well, we might as well not go sample it, right? We're not going to be mining in the national park, for instance. So we look through this rubric, we identify where there's existing data and where the data needs to be augmented. And then we take an approach of like, hey, are there high throughput screening tools we can use? So my colleague Richard Bishop is a drone expert, and he's trying to research if we can use certain sensors on drones to get early indication of potential critical mineral or rare earth mineralization. And if so, then you can follow that up with more detailed sampling and analysis and things like that. So large study area, large material scope, but enables us to begin to identify and to an extent quantify what we're calling the critical mineral endowment through our region. And then, in their wisdom, DOE now has an awardee in every region throughout the country. So every part of the country is reflected by one region and or has a representative region there. And then, they're all taking similar approaches, I would say, with that charge of understanding the critical mineral endowment.
That's really interesting. So two follow-up questions to that is, one, what's the lifespan of this project, and how far are you able to last with that funding? And then two, is any of that funding being used to incentivize students to join the program and further their education there?
No, a really good question. So the the question on timing, the current effort is a 3-year project, which is a pretty typical lifespan for most of our projects. Most of the funded work we do is on this 2 or 3-year time horizon. So 3 years is about right. This is coming off of, they had an initial phase one a couple years ago. And in phase one, they had a lot more regions. It was scoped a little bit differently. And the overall magnitude of the projects were much smaller. So we were on one of the phase one awardees, and now we're on this phase two. So phase one was 1.5 to 2 years. This phase two is now 3 years. And yes, no, I mean, the student facing portion of this, as with any of our R&D programs, is an important, but I think also like underappreciated value of what we're doing. So a big portion of any research project we do involves direct graduate student support. So if any aspiring graduate students are listening to the podcast, please know you can get your education paid for and learn quite a bit along the way in a really awesome area. So there's my plug for joining Virginia Tech's graduate program. We also have a really big emphasis on undergraduate research here. So within my research group at any time, I will have multiple undergraduate researchers, sometimes as many as 10. I think one summer we hired 10 undergraduate interns just in my research group. And a really good opportunity, I would say, to get your hands dirty, to learn a little bit more about a topic, to interface with graduate students and research professionals, and then also, get excited about the field. One of the big components of my particular research group is I take a very interdisciplinary approach. So when I am seeking to recruit undergraduate students, graduate students, and then postdocs, I don't constrain myself to mining engineers and metallurgists, but I want to see students who have an interest in chemistry, an interest in geology, an interest in mechanical engineering and electrical engineering, chemical engineering, right? Let's span the gamut to try to get as many people interested in the field as possible. So for example, right now we have one chemistry student working with us. And in her presentation she gave a couple weeks ago, she said, 4 weeks ago, I had no clue that any of this existed. And now I think it's one of the coolest projects to be working on. And to me, that's such a win for what we're doing. And it's like, I wish we could do that every time we have the opportunity.
So on that question about Virginia Tech, and I know there's an ecosystem of universities that are teaching mining, metallurgy related. Could you share a little bit about just Virginia Tech and why they're so important? It's a good time to be also promote the university. Like, what is it? What's special about Virginia Tech? Why do we hear such good things about it? And what's your focus, and what are some of your other colleagues' focus? Just so we can have a better understanding.
No, Virginia Tech. So I think, I'm a 3-time alum of this program. And then I've been a faculty member here for about 10 years and a department head for 3 years. I'm wearing my Virginia Tech tie today and my Virginia Tech lapel pin. So I bleed orange and maroon, right? And so I think Virginia Tech, we have a very passionate alumni and student base, and you'll see that a lot out there. But I like to say, the Virginia Tech, most people don't think of Virginia as being, the center of mining, right? Or a big mining hotbed. And most people don't even know Virginia Tech has a mining engineering program. So when I talk to people on the streets, right, and I tell them I'm a mining engineering professor at Virginia Tech, you get a kind of a surprise reaction. But in seriousness, mining is kind of like ingrained into the Virginia Tech culture, going back to the very beginning. And I like to say that the fun fact, the very first engineering degree awarded here was in mining engineering, I believe in the 1870s or 1880s, like over 100 years ago. And over that time, I think we've had a really strong commitment to serve the industry, to serve our students, and to really recruit top talent across the board in every facet. So we want talented students, we want talented faculty, we want talented leadership. And certainly, I think that's what makes us distinct today, is our ability to convene talent and then to resource that talent, right? Whether we think about faculty, students, graduate students, to resource that talent to be impactful. And so when we do projects, right, and we talk about these research projects, we know at the end of the day, that's going to have an outcome for some constituency. And so if we're going and doing the Expand App project and trying to understand the mineral potential of Appalachia, that is so hopefully one day we can create jobs in Appalachia so people can be gainfully employed and contribute to society, right? We want to do this for an impact in the end. And I think that's something that makes our department very unique is that obviously the scientific work, the publications and all that will happen, right? Like we will generate new knowledge and we will report that knowledge, but we are very, very focused on impact. So what is the impact? What is that knowledge going to do or going to accomplish? And that's kind of baked into our culture. Like I said, if you go back to over the years in the 1950s, right, one of the Virginia Tech researchers here came up with a very famous equation for quantifying the strength of coal. And this is what essentially led engineers to be able to design coal mines that don't collapse, right? So they were able to come up with this equation to quantify the strength of coal. So now we can design underground mines that stay supported. And that formula is still taught today. So it's still part of an undergraduate curriculum today, but started here at Virginia Tech. If you look at our faculty, so right now we would say we have like 11 faculty in the mining and minerals engineering department. I would say about 4 of those kind of sit on the processing side. So how do we extract and recover minerals? A lot of focus in critical minerals and novel technology. That's kind of that focus area. The remaining faculty sit in what I would call more traditional mining disciplines. So upstream, how do we identify and extract resources? How do we coordinate technology and people and systems? And then also that still thread of health and safety. How do we ensure that we're doing the work that we are in a way that's going to benefit the workers? So connecting the dots there, right? We have one of our really great researchers now is looking at, say, coal mine dust, right? And trying to understand why there's prevalence of increasing black lung and then trying to find ways to mitigate that. So you go back to the 1950s, we were, developing formulas to make mines safer for workers. Today in the 2020s, we're looking at coal mine dust to make mines safer for workers. So all that kind of to summarize it, I think what makes it special here at Virginia Tech is our focus
And that's
on
very,
impact.
very powerful. The programs are and that's what we pick up on and hear through the market and the various networks that are in these industries, that your program is very good at connecting to real world scenarios. And we know you have dozens of projects with companies and so forth that you're working on. On that note, let's talk about what is needed. So one of the challenges that we've run into, and would love your feedback, critical feedback on this, we are finding that even with the amount of capital that's being allocated from Washington, which is great. I mean, I think the government's woken up to a lot of these challenges. There still seems to be a lack of emphasis on, education, workforce development, talent development. Is that a real issue? How can we, and if it is, how can we use Virginia Tech and other universities to start to raise awareness to get more people involved? Because I think we do have to reindustrialize here. And so we're going to need people.
No, Dan, that's an exceptional question. And, if you're a hammer, you only see nails, right? So if you're a professor, you're going to see problems a certain way. But, a couple layers to this. One, I like to think about the enabling system, right? What is it going to, and what's going to be needed to enable sustainable and robust production of rare earths and critical minerals in this country? And underneath that enabling system, there's obviously resources, right? We can't mine if we don't have the resources. There's technology. If we can't innovate and produce the best technology, we're not going to be able to compete. There's also talent. And I think from my standpoint, talent is the most critical. And I think they're all critical, right? It's like the critical mineral list. There's so many of them, they're all critical, but they're all important. But to me, the talent is the one that is often overlooked. But absolutely essential. The last one I always put in is also coordination and alignment. So we need resources, we need technology, we need talent, and we need coordination and alignment. And that is how we define the enabling system. But let me take another angle to this. And I've thought a lot about this, and I think about the critical mineral challenge, right? And the rare earth challenge in this country. And I think often we are actually confounding 2 challenges. And what I mean by that, so one challenge is this acute need, right? If we were facing a real supply shock, and you could argue that we're facing that now, how do we produce what industry needs in a very rapid time period and for a fixed duration? And how do we produce over the next 3 years enough to meet industrial needs? That is one challenge. The other challenge is how do we develop the enabling system that sustains us over decades, like 20, 30, 40 years, right? And when you separate those two, you begin to realize, for instance, in the short term, capex doesn't matter, right? It's like if we're facing acute need,
Right.
supply security matters, right? Over the long term, you could say cost is all that matters. And so in solving that, when you break that down, you begin to realize are the strategies we are taking trying to solve both challenges at the same time. And this looping back to this talent question, right? Right now in the US in mining and minerals engineering, nominally you could say we're graduating 200 people a year. So we're sending 200 across the country, 200
Well, Aaron,
engineers into
just to
the
clarify,
into
so
the
that's
ecosystem. Yeah.
200 Virginia Tech or 200 nationwide?
All right. I wish it were 200 Virginia
Wow.
Tech. That is 200
Wow.
nationwide. So across the nation, across the nation, 200 mining engineers. Virginia Tech, we produce 15 to 20%
Just out of
of that in a
curiosity,
given
what would
year.
that compare to India or China?
In China, it's like make sure you're sitting down. Hard to tell. That
Mm,
number's probably over
wow.
10,000. So that said, like
Wow.
we are not even close, right? And a couple weeks ago there was a Reuters article that talked about degree specialization in China as well. So here in the U.S., going back to the cake analogy, we by and large train generalists, right? That can go work in crushed stone, in iron ore, in base metals, perhaps in rare earths if there's opportunity. Because of the scale, right? In China, they produce specialists. So they would have degrees in rare earth, like in rare earth mining and processing. Whereas here, we don't have that degree of specialization because we don't have the same scale. And so how this trickles down, right, over the 30-year horizon is, that lack of talent becomes barriers to innovation, barriers to project development, barriers to operations. And so if we want to meet our critical minerals ambitions, what I tell people is, okay, if we want to meet all these goals and targets and we need to really intensify production, who's going to operate all those plants? Who's going to design the mines? Who's going to innovate the next generation of solutions? Going down, who's going to permit those mines, right? And so every layer where you don't have people trained in the subject matter, it creates friction in the system. And then that friction compounds. And then that's what really inhibits you over that 30, 40, 50-year
So
time
this is a
horizon.
very important point. I mean, and you just informed me on something. I had no idea that there are that few engineers being graduated every year. It's really striking. So yes. Now let's talk about. I know you're in the university system, and it's very important. But let us also talk about the state college system, the community college system,
Mm.
and even the technical school. Private technical schools. If the president of the United States came to you and said, I want to accelerate a workforce army of trained, educated professionals across the value chain, from upstream mining to midstream separation, metallurgy, to downstream magnet production. Would there be some blueprint you would think about?
I don't know if I have a blueprint, but I would say the pieces are there to do that, right? I think what's needed is the motivation and the alignment. And I know, like, most of the universities, we do have partnerships with the local community colleges, with the trade schools. They're not always leveraged as well as they could be, right? And especially in the mining and processing space. And sometimes I think it's demand driven, right? The notion here is there's a mismatch between what the industry needs and what the students are interested
Right.
in, right? What the student demand is. But if you could get that student push, right, that goes along with the industry demand pool, then I think there's the pieces are there to align top to bottom on your, from your PhD caliber, innovation, leads to your practicing engineers and metallurgists, to your frontline workers, to your welders and tradespeople and everything below that, right? So I feel like there's the pieces there. How you pin them together and how you align them is something that I think
Understood.
needs further consideration.
Very fascinating.
Yeah. I think one question to wrap up the show here today really quick is I would like you just to talk really quick about the Aclara Resources project. You guys have a facility on campus now, and I'm always intrigued when the commercial meets education at the same level. So what is that doing for you guys to further the work?
No, thanks for asking that, Dustin. And the Aclara partnership has been one that we've been very proud of and very pleased with. And last March, they had their ribbon cutting ceremony there. And I would encourage your viewers, shameless plug here, if you get the opportunity to go watch the speech I made at the ribbon cutting ceremony, I think it captures a lot of what makes that partnership so special. And tying back to the theme of the last question, right? It is really an investment in people. And that's what I said in my talk for the ribbon cutting was that, the I think the statement I made is that, supply chains aren't built by workshops. They're not built by university professors, right? They're not built by podcasts, even though I love this podcast. At the end of the day, they're built by people, right? If we're going to develop and build the rare earth supply chain in this country, it's going to start with people, which is going to necessarily require an investment in people. And one of the big challenges, right? One of the big fundamental challenges in this space is you're essentially trying to start from scratch, right? And it creates this chicken and egg dichotomy, right? This chicken and egg issue where in order to design and operate real processing plants that can do the complex separation, the complex chemistry and all that, you really need to have experienced people who know how it works, know how it works at scale, knows where there's going to be hiccups and challenges. You need practitioners who have seen it and felt it and tasted it. But because we don't have any production, then there's no proving grounds for those people to be trained. Right. So it's like now you don't have the people to do the design because you don't have the facility. And because you don't have a facility, you don't have a way to do the design. So it creates a really, I think, negative feedback loop, and one that, frankly, in this country, I think it's one of the big challenges. And I've sat in meetings before and said, if you're wanting to design a heavy rare separation plant, there's probably less than 10 people in this country who can do it and do it well. Right. Like less than 10. And we'll be sitting in rooms with 40 people. And I'm like, yeah, it's like less than the people in this room or the people I would trust to actually do this well. And so what that relates to then is I think Aclara made an intentional investment to partner with the universe, with this talent pipeline being a big component of that. So right now we have students and researchers who work there every day. They get opportunity to see how the equipment works. They get the opportunity to see how what they're learning about in the classroom actually translates and actually looks like, and doing that in a facility that's not simple, right? We call it a pilot plant, but it's actually a demonstration. I would categorize it as a demonstration plant. It looks just like an industrial facility, except it's smaller, right? But the way it's connected, configured, the way it's instrumented is all very similar to what you'd see in industry. And so that hands-on experiential learning has always been a hallmark of the Virginia Tech educational experience. And this is really a great way we've been able to bring that to life here in the critical mineral space.
That's fantastic. And I think it's exciting to hear, like I was saying, when commercial businesses are interested in being a part of the educational experience, I think there's only one way, and it's up. So I think that's great. Aaron, thank you for being on the show with us. I think you gave us a lot of great insight and opened our eyes and our minds to kind of what's going on from an education perspective, but also from an industry perspective. Hopefully we'll have you on the show again to give us an update and provide more insights as things progress. Because you even said earlier, in the last year, a lot has changed and shifted. And so I would imagine over the next 12 months, we're going to see even more. So, but thanks again.
Thanks, Aaron.
Excellent. It's been a pleasure. Thank you.